So the first and foremost thing is that we understand what sinusoidal waveforms are. So sinusoidal waveforms are represented by an equation like this. A of t is a function of time, which is equal to A max, the maximum value, times cosine of some omega t plus phi a. So in here, phi is called the basically angular frequency of the system, which is 2 pi times f, where f is the frequency. And phi a is the phase angle. A max is the maximum, right? So this is going to be a representation of a sinusoidal waveform. A of t is as a function of t. It would be something like this. A period would be basically equal to 1 over f, and that's the time frame in which the waveform repeats itself over time. When the omega, or the frequency of the waveform, is constant, we can represent basically the sinusoidal waveform through a phasor representation. So the phasor representation of what you saw, A max times cosine of omega t plus phi a, would be something like a RMS with the angle of phi a. So we show A of t in the time domain. We show A bar in this course to represent basically the phasor. And the RMS value of the phasor of the waveform would be just the maximum value over a square root of 2. So that's the phasor representation that we do in this course. So you can see that omega or f has not been explicitly indicated in here. And when we represent a sinusoidal waveform through its phasor, we implicitly indicate that. We're assuming that the frequency is constant when we know it. Yeah, a phasor can be algebraically can be treated as a vector because it's something that has an angle and a magnitude. So you can represent that on a complex plane using basically a vector and do the same type of algebraic summation, subtraction, and so on as you do on vectors with a phasor as well. So an example of a circuit, an RL circuit, has been shown in here. We have a voltage source that has been connected to an R and an L in series, a resistance and an inductance. Now, if you want to come up with the solution of this network, to come up with the solution of I of t, for example, the current that flows inside your network, there are multiple ways that you can do that. You can do the calculation in time domain, which means that you can write up the differential equations associated with this network and then come up with the solution to find out I of t. You can apply, for example, a Laplace transformation, come up with the basically solution of this network using a Laplace transform. But an easier way to deal with the solution of this problem is to use phasor analysis. So phasor analysis is a type of analysis that you do on your sinusoidal networks. And by a sinusoidal network, we mean a network that has sinusoidal sources, right? And a bunch of R, L, and C elements. So this type of network can be analyzed through a phasor analysis if we are not interested in the transients of that network. So when you do solve a network, we all know that it has basically a transient response that happens at the very beginning. When you energize this circuit, you would have a transient response associated with that. But as the time goes through, you get to a steady state portion. And by a steady state portion means the portion that repeats itself for a sinusoidal network, repeats itself. The voltages and currents would basically have the same pattern over time. They don't change basically their magnitude. They don't change their angles. So it would be the voltage and current would look like something like this. They repeat themselves over time. So this type of behavior is when you reach a steady state. And once you reach a steady state, then instead of dealing with these types of circuits using time domain solution or Laplace transformation and so on, you can deal with it through phasor analysis, meaning that instead of dealing with differential equations, now you can write up the KVL and KCL and do algebraic equations instead of basically differential equations, and that would be a much easier way to deal with the solution of this problem. But the catch is that you obviously don't get the transient response. So in the occasions that the transient response is important for you, then phasor analysis is not good. But when you don't care about the transient response and you just care about the steady state response of the system, then your basically phasor analysis would be enough. So in order to deal with this network through phasor analysis, you need to write up all of your sources in the form of their associated waveforms. And then the RLC elements need to be converted into their impedances. So at the end, you would have some impedance that is connected to a source. And then through that, so for example, in this network, this V of t is converted to its phasor like this, equation 1, 3. And then the whole network can be represented by an equivalent impedance, which in this case, that would be R plus JL omega, where L was the inductance and omega is the basically omega of the source, which would be happening in the whole network. If you have just one frequency in the whole network, then that would be expanded to all the voltages and currents that are in that network. So this Z bar becomes the impedance of our network, which would have an amplitude or magnitude and an angle of phi of z. Then you can come up with the Ohm's law very easily to divide the voltage over the impedance to find out the phasor of the current. Now, once you find the phasor of the current, it would have a magnitude, it would have an equivalent angle, right? So you can then say that in steady state, your time domain waveform would be basically this magnitude of the phasor times square root of 2 to make it the maximum value. And then you would have a cosine of omega t plus this basically angle that you solved for in equation 1.15. When you have a network, you can have a few definitions associated with the power. So the first definition associated with the power would be the instantaneous power. So let's assume that you have an impedance, you have provided a voltage, and because of that voltage provided to that impedance, there would be a current flowing into that impedance. Now, if you basically multiply V of t by I of t, you simply get the instantaneous power. And if your network is a sinusoidal network, we know that the voltage and current would basically be of sinusoidal forms. So the instantaneous power would be just the product of these two sinusoidal voltages and currents, right? So this would be your instantaneous power. Keep in mind that the definition of instantaneous power is quite general, so it can occur, the instantaneous power would be associated with any network, with any type of voltage sources and current sources. But in the case of a sinusoidal network, basically we would know that the voltage and current would be also sinusoidal for any element. Therefore, the instantaneous power would be the multiplication of the voltage and current sinusoidal forms, and it would get you something like this. If you go ahead and use the trigonometry identities, you see that the sinusoidal, instantaneous power for your sinusoidal network would be of this form that is shown in equation 110. And in equation 110, V and I are the RMS values of the voltage and current, and phi is the phi V minus phi I, where phi V is the angle, phase angle of the voltage, and phi I is the phase angle of the current. Okay, so this is sinusoidal, this is instantaneous power in a sinusoidal network. Now, if you look at basically this equation 110, you see that it is consisting of a few parts. So one part is this. So this is just a sinusoidal, basically, waveform, which has this maximum value, right? And this is also, this term is getting this VI cosine of phi, is getting multiplied by 1. So we could expand this. It would have a VI cosine of phi times cosine of 2 omega t plus 2 phi v, which would be, again, a sinusoidal waveform. And when VI cosine of phi gets multiplied by 1, it becomes a constant number because phi is constant, V is constant, and I is constant, right? So if you can basically expand this, you would see a term of VI cosine of phi, which would be a constant value, and plus two sinusoidal waveforms. One is VI cosine of phi times cosine of this angle, plus one is VI sine of phi times this. So active power would be the term associated with that constant part. So we call that VI cosine of phi the active or real power. And that would be the power that would be consumed or generated based on the type of element that we have in here, right? So in here, we have the load convention, and based off the load convention, the current would flow into the positive terminal of the element. So this is called the load convention, when basically the current flows into the positive terminal of the voltage of the element. Then this p-value would become the real or active power that is consumed by this element. Okay, so we would have a real or active power definition, and we would have a reactive power definition. Reactive power definition is just VI sine of phi, which is the maximum of this waveform, that we call it Px of t. So Px of t would be VI sine of phi, sine of 2 omega t plus 2 phi v. This maximum value of it would be called the reactive power. And if you look at the first term here in the instantaneous power, the first term is called PR of t, which is VI cosine of phi times 1 plus this cosine term. This PR of t has an average, a value equal to VI cosine of phi, which you call it what? The active or real power. All right, so what is the difference between active power and reactive power? The active power is just a term that in this case is going to be consumed on an average basis, is going to be consumed by your load. So this means that if this is a load, there should have been some generator somewhere that provides that power to your load. So your generator is generating that power, your load is consuming that power on the average over time. So this is the representation of some work that is being done in your network because of the actions of the generators and your loads. Your generators would generate that certain amount of power on average, and your loads on average would consume that load. So this is called the real or active power. But what about reactive power? So first of all, can you tell me when that reactive power happens? When you have an overall capacitive or inductive network. Because only in that case is when, look at this phi. If this sine of phi is 0, it means that phi would be 0, right? And what was phi? Phi was the angle difference between the voltage and the current. So if your network is completely resistive, if you have a network that is completely resistive, so this means that you have a source and a bunch of basically combination of resistances. Then, so the voltage that you have over here, V of I, versus the current that is flowing in this network, they would be on the same, they would have the same phase angle. This means that, for example, if V of t is 10 cosine of omega t plus 35 degrees, then I should be something like, for example, 0.2 cosine of same omega t plus 35 degrees. So this is called phi of v. This is called phi of I, right? So phi v minus phi I becomes 0. In this case, your network is purely resistive. Now, if you have a network that is overall working like a combination of resistance and inductance, in this case, then if V of t is, for example, 10 cosine of omega t plus 35 degrees, then I of t should be something less than that in terms of phase angle. That's when we say that the current is lagging the voltage. So instead of 35 degrees, it would be something like 25 degrees. So in this case, when the angle of the current is smaller than the angle of the voltage, we say that we have a lagging power factor. We have a basically load or a network that has a lagging power factor because the current lags basically the voltage. In that case, current is behind the voltage. But if you have a network that is a combination of overall resistance and capacitance, then the angle that you find for your voltage would be ahead. So instead of 35, it is, for example, 45 degrees, the angle of current. In this case, the angle of current would be greater than the angle of voltage. So we would have a leading power factor in this case in our network. So you can see that reactive power only happens when you have a leading or lagging power factor, because that's only in that case where phi would be non-zero. If your network is purely resistive, phi would be zero and there would be no sign of reactive power. Capacitances and inductances, if they're ideal, they do not basically consume power or generate power. They just exchange power. So we have a bunch of elements in the network that are the sources, our inductors, and our basically capacitors and our resistances. So reactive power is the representation of the power that is going to be exchanged between these three elements: the inductances, the capacitances, and the source, the power that just circulates between these without doing any work. So overall, on average, there would be no power consumed or generated in between basically sources, inductances, and your capacitors. So their action would not be basically causing any power loss. But the only elements that can produce and exchange the real or active power would be your sources and your resistive elements. So in order to show that you have a network that, although you know that capacitances and inductances are not consuming power, they're just exchanging power, but in order to show that those elements are existing in your network, you have to come up with another basically definition of power, which you call it the reactive power, if that makes sense. So reactive power is a type of power that is not consumed nor basically generated. It's something that is just exchanged between the sources, capacitive and inductive elements. All right, so there is an example in here. In this example, we have like a single phase load with this impedance, which is connected to a sinusoidal source with this much of voltage. We want to determine the instantaneous current, instantaneous power, and we want to plot all of this. So the solution has been here. I don't go through the solution. I just want to show you basically the results. So this is P of t, the instantaneous power. If you compare it with zero, you see that the instantaneous power has some average, right? And that average would be called the average power or the real power or the active power. Active power would be the average of the P of t. Now, we are showing the basically voltage and current. So voltage has been shown with the blue and the current has been shown with the green. And you can see that they are both sinusoidal. Both voltage and current would have an average of zero, but there is some phase shift between them. So when you have a maximum basically voltage, is the time that you have the maximum voltage is different from the time that you have your maximum current, right? So this is showing that phase shift. Now, if you recall, we divided the P of t, instantaneous power, into two parts. That instantaneous power was divided into two parts. So this part, we called it PR of t. And this part, we called it Px of t, which is in here. So we've been plotting both of these components as well. So you can see that the PR of t is non-zero. At all times, it's above zero. It has an average. The average value would be the same active power. So this 2000 should be the same that you get in here. The average of P of t should be the same as the average of PR of t. And this is Px of t, the reactive basically representation, reactive power representation. You can see that it's a sinusoid, which has a zero average. But to show how big basically your reactive power in your system is, you look at the maximum of this waveform. So the more this is, it shows that your system basically has more basically inductive or capacitive elements inside it, if that makes sense. Now, I talked about the load convention. Load convention was when you had an element where the current would go into the positive polarity or positive terminal of the voltage. On the contrary, when the current comes out of the positive terminal of the voltage, this is called the generator convention. So keep that in mind. We have generator convention, we have load convention. So when you define the instantaneous power for an element that is represented by generator convention, then what you get is the instantaneous power generated by that element, whatever you come up with. Same calculation if you do for this element, which is based on the generator convention. If you find the active power to be positive, it means that that element generated that amount of power, right? So whatever you come up with is a generated value by that element if your element has been represented by generator convention. On the contrary, whatever value, whatever calculation that you come up with, if your element has been represented by the load convention, would be the value that has been consumed by that element, not generated. Now, let's go to the definition of complex power. So complex power would be just when you put the active power plus J reactive power, that becomes the complex power of your element. And the apparent power would be the magnitude of the complex power. So if this is active power, P, and this is reactive power, Q, if you just combine them together, that becomes the complex power, where complex power is a complex number, as the name shows. The magnitude of the complex power, which is S without bar, is called apparent power. So this is called complex power. The magnitude of that is called the apparent power. So in order to show that through math of the voltage and through the voltage and currents, the complex power is defined as the voltage times the conjugated value of the current phasor. The conjugate value means that you have to put the angle with the negative sign, right? So that becomes the complex power. Yeah, the active and reactive portions here join together to form the complex power. So these are all different representations of complex power. And then the apparent power would be the magnitude of the complex power, which would be equal to square root of P squared plus Q squared. And we have this angle called the power factor angle. Phi V minus phi I is called the power factor angle. And the cosine of phi would be called power factor. Yes, power factor would be the cosine of that angle. Another representation for power factor would be the cosine of the arctangent of Q over P. So if you have an element that you have its reactive power and its active power, go get the arctangent of Q over P, and then that becomes your phi. The cosine of the arctangent of Q over P becomes your phi value, and then the cosine of phi becomes the complex power, which is also equal to P over square root of P squared plus Q squared. If an element is shown by a load convention and you calculate the consumed reactive power and find that reactive power consumed to be positive, then that load would be a reactive load, which means that it's overall acting as an inductive circuit. If you calculate that consumed reactive power and you find it to be negative, then it means that the load is capacitive. Now we can have other statements for complex power of a load. So if you have a single phase load with an impedance of R plus JX, and the phasors of the voltage across it and the current through it are V bar and I bar, then we know that based on the Ohm's law, V bar should be equal to Z bar times I bar, right? Now, based on this, the complex power, we know it's equal to the complex power of that load is V times I conjugated. So you can, instead of V, put Z times I. Now you have Z I conjugated, which becomes when I bar gets multiplied by the I conjugated, that becomes I without bar squared. I without bar means magnitude of the current. Without bar would be the magnitude of I bar. V without bar would be the magnitude of the V bar. That makes sense. So therefore, in order to find the complex power associated with a load, the complex power consumed by a load, you can basically find its active portion value by R times I squared and its reactive portion by X times I squared, where R and X are the resistance and reactance of that load. Based on the same basically definition of complex power, instead of now I can put basically V over Z. Then that becomes V squared over Z bar conjugate. So complex power of the load can be found by either of these statements as well, as you can see on the screen. Keep that in mind. This V is without bar, which means that it's only the magnitude of the voltage. Complex power balance is nothing but another representation of the conservation of energy. It means that if you have a sinusoidal network, if you can divide it by sources and loads, then the sources would be represented by the the generator convention, right? This is the source, which is represented by the generator convention, which means that the current comes out of the positive terminal. And all of these loads would be represented by their load convention, which means that the current goes into their positive, basically, terminals, okay? So you divide your network into a bunch of sources, into a bunch of loads, then based on the complex power balance, the complex power that is coming or is being generated by all of your sources should be equal to the complex power that is consumed by your loads in your system. So when you divide your system into sources and loads, representing the sources through the generator convention, the complex power generated by those sources would be coming as, for example, 10 plus 5J, then that should be equal to the complex power that is being consumed by your loads in your system when they are represented by load convention, obviously. Power factor correction. Let's say that you have a source, sinusoidal source, a transmission system, and a load. Okay, this is like what we have in most of power systems. You have a transmission system, right? Now you find the power factor of this load. In most cases, power systems are in a way that you have inductive loads. So for the most part, you have basically lagging power factors in your power systems, which means that you can basically represent your load as a combination of resistances plus inductances, right? So the bad thing about your systems to be too much inductive is that we know, for example, if this load is 10 megawatt plus J 8 megavars, okay? Based on its nature, this load is consuming 10 megawatts of real power. So that's nothing to argue about. That load needs this power to be provided by generators in your system, and you have to provide it. Otherwise, your load cannot work. But what about this reactive portion, the 8 megavars? Is that good? I mean, is that good to be too much inductive? Knowing that all of these basically reactive powers are basically a representation of those energies that are just exchanged in your system without getting consumed anywhere. So this means that this 8 megawatt, not only you have to provide 10 megawatt through this source, through this transmission system, but also you have to provide 8 megavars that is just circulating in your network without doing any good, right? So therefore, and yet this 8 megawatt also needs to be exchanged between your load, your basically transmission system, and your source. Which means that if you have a transmission system of like 100 kilometers, you have to provide that 8 megawatt through this source and then pass it through this 100-kilometer transmission system, which will add up to the losses of the system. So having your power systems this much inductive is not good. In order to resolve that issue, you come up with a concept of power factor correction, which means that instead of providing the reactive power requirements of your load through far away, through your source, which is 100 kilometers away, you try to basically provide that locally to this load. And how is that possible? If you put a capacitor right in parallel with your load, that will do the job for you. Capacitor's job is to, in fact, generate reactive power. So for inductive systems, the consumed reactive power would be positive, but for capacitive systems, the consumed reactive power would be negative, which means that capacitive systems, in fact, generate reactive power. So if we are able to basically provide, for example, instead of 8 megavar, provide 4 megavar of it through your local capacitor, overall, your load would be now consuming 10 megawatt plus J 4 megawars, right? Now, instead of 10 plus J 8 megavar, it would now consume 10 megawatt plus J 4 megavar. Now, tell me the math. What would be the cosine of, what would be the power factor in this case, the first case? Power factor in the first case, non-compensated. We have the equation in here. The power factor is P, which is 10 over square root of 10 squared plus 8 squared, right? Power factor in the first case. Power factor in the second case would be 10 over square root of 10 squared plus 4 squared. So let's do the calculations, 0.78. In the second case, it's 0.92 or 93 almost. So you can see that you are improving the power factor. Power factor correction is to make the power factor as close as possible to 1. This is why we have capacitor banks, because we want to improve the power factor as much as possible in order to avoid transferring a lot of reactive power for our loads through long distance places, because that adds up to the overall losses of our systems. Okay? So that's what we mean by power factor correction. Power flow through an impedance. So if you have an impedance of R plus JX, you have an impedance, then you have 2 voltage sources on the 2 sides, or 2 voltages on 2 sides. The power that goes from left side to right side is called P12 for the active portion. For the reactive portion, that's Q12. And from right to left, that would be P21 and Q21. Now, using V1, delta 1, V2, delta 2, Z, and gamma, you can come up with those basically active and reactive powers. If you're looking for the losses in your system, then you can basically add up P12 to Q12. P12 plus P21 plus P21, that becomes the active power losses in this path. If you add up Q12 to Q21, that becomes the reactive power loss in this path. Okay. Now, if R is 0, what would be the active power loss in this path? No losses. Losses would be 0, correct. So in that case, we would get an easier, basically, when R is equal to 0, P12 would be the negative of P21, and Q12 and Q21 are still basically not equal to the negative of each other. So keep that in mind. And now I have a question for you. What happens if you come up with the reactive power losses, you add up Q12 to Q21, and you get a negative number? What does that mean? So, in other words, I'm asking you, can reactive power losses in this path be negative? Those who said yes are correct. We could have negative reactive power losses in this path. In that case, it means that we are not consuming reactive power. We are, in fact, generating reactive power. When does that happen? So if you have an impedance that is too much capacitive, it will create or generate reactive power for you. So in that case, you wouldn't have the consumed reactive power could become negative. So keep that in mind also. So for the most part, our discussion on three-phase systems would be for balanced three-phase systems, which means that in a balanced power system, wherever you have something about phase A, in terms of voltage and current, the voltages and currents in the other 2 phases would look like exactly the same, just with 120 degrees of phase shift, in the sense that phase B would be behind phase A by 120 degrees, and phase C would be ahead of phase A well, for 120 degrees. So this is what needs to be realized for balanced power systems. These MA, AB, MB, and MCs could be for voltages and currents, both. So in that case, when you're adding up the the corresponding three-phase voltages or currents in the same point in a system, their sum would be 0. So this is a good sign of whether a power system is balanced or not. Get the measurements for the same node, for the 3 phases of the same node, add them up together. If the result is small, then it means that the system is balanced. Otherwise, the system becomes unbalanced. And when we're talking about basically the 3 phasors associated with the 3 phases, if this is MA, then MB would be 120 degrees behind, and MC would be 120 degrees ahead. This is all with respect to counterclockwise rotation. So this means that we're assuming a positive rotation to be counterclockwise. So when we say MB is behind MA, it basically means that you have to travel for positive 120 with respect to the counterclockwise rotation to reach MA. And when you say that MC is ahead of MA, or in other words, MA is behind MC for 120 degrees, it means that with respect to counterclockwise rotation, you have to travel another 100 plus 120 to reach MC from where you are at MA. And to show that basically phase shift, we use an operator of alpha, which is nothing but 1 with angle of positive 120 degrees. So this angle is always used to show the relationship between the 3 phasors in the 3 phases. So with that respect, MA would be 8 alpha times MB, would be alpha squared times MC. A squared means 2 times A, means 240 degrees of phase shift, which would be the same as minus 120 degrees, right? Now, if the system becomes unbalanced, this basically means that either this phase shift is not 120 in the sense that we expect, or the magnitudes of basically the maximum values of those sinusoidal waveforms are not exactly the same. If either of these things happen, then the system becomes unbalanced. Now, talking about 3-phase loads, so this is how basically a 3-phase load would look like. We could have either a delta connection or a Y connection. So if you're having a delta connection, basically, this means that the ABC, consider the ABC terminals. There would be an equivalent impedance between A and B, B and C, and C and A, which we call them ZAB, ZBC, and ZCA. In general, ZAB, ZBC, and ZCA could be different from one another. In that case, the case that your load is unbalanced. But if your load is balanced in the sense of balanced loads, all of these 3 legs must be equal. So ZAB must be equal to ZBC, and that must be equal to ZCA. Now, what do we call these currents, IA, IB, and IC, that are flowing in the line? These are called the line currents. The currents that are flowing between phases, like IAB, IBC, ICA, these are called phase currents. Now, when you're connecting a load in a Y fashion or a star fashion, then the line current would be the same as the phase current. And basically, this VAB, the voltage between AB, BC, and CA, these would be called line voltages. But the voltages from A to neutral, B to neutral, and C to neutral, they would be called phase voltages or line to neutral voltages. If your system is balanced, the relationship between VAB, VBC, and VCA would be that they would be all equal. And when we say VAB is equal to VBC, equal to VCA, and I'm not including the phasor on that, it means that I'm talking about the magnitude only, right? So in magnitude-wise, they would be equal. And when you want to compare them with the line to neutral or phase to neutral voltages, that would be square root of 3 times of that. Square root of 3 times VAN, VBN, VCN. You can see that if we have basically neutrals available, neutral points available because of the star connections, then we could have impedances connecting those neutral points. But if your system is completely balanced, whether or not you put that neutral cable or neutral conductor between the neutral points really doesn't matter because those will not carry any currents. That's because if the system is balanced, the sum of these three currents would be just zero. They don't get a chance to pass through the neutral impedance. But obviously, if the system is not balanced, that's not the case. There would be some currents flowing in the neutral impedances, and that's one of the signs that you can see that your system has become unbalanced. Okay, so we can also talk about delta Y transformation. And delta Y transformation is quite general. It doesn't matter if the system is balanced or unbalanced. What we mean by delta Y transformation is that if you have like a delta connected load with ZAB, ZBC, ZCA values, which could be not equal, you could convert that delta into a Y and calling the impedances ZAN, ZBN, ZCN. You can find those three ZAN, ZBN, ZCN impedances in a way that the same voltages would fall on the terminals of the load in both cases. The same line currents would flow into the three terminals in both cases. Okay? If you can basically do that, it means that you found the equivalent Y from the delta or vice versa. So if you want to find the Y equivalent from the delta impedances, this is how you can basically do that. Transformation can be from can be converting Y to a delta. The only difference is that you have to, if you want to use the same formulation, then you have to convert the impedances to admittance values. Then you would find the admittance. And obviously, when you find the admittance, it means that you can get the reciprocal of that to find the impedance. Looking at ZABC, and this would be ZAB, ZBC, ZCA. This would be ZAN, ZBN, ZCN, right? So to find ZAN, you would look at the side impedances, ZAB times ZCA, divided by the sum, ZAB, ZBC, ZCA. The other conversion would be from a Y to a delta. In that case, if you want to find ZCA, you would find YCA first. How you would find YCA? You would find YCA from those star components on the sides of it. But again, use the Y's. So YAN times YCN, and then divided by the sum, YAN plus YBN plus YCN. So this way is easier to understand because they work the same way, except that you have to remember, if you want to find basically the Y components, that would be found from the impedances. If you want to find the delta components, that is found from the admittances. And then we can extend the same power definitions that we did for the single-phase system to three-phase system. So in that case, it means that if you're talking about a delta-connected, for example, component, then the instantaneous power would be the sum of the individual instantaneous powers in every leg of that, or every side in that delta-connected component, which means PAB plus PBC plus PCA. And obviously, PAB would be VAB times IAB, and so on and so forth. If the component is Y-connected, then you have to do basically, again, the same PA plus PB plus PC, or VAN times IA plus VBN times IB plus VCN times IC. If you want to find out the active power, then the active power of that component, if the system is balanced, would be found from 3 times of the individual single-phase components. So when we're having, for example, if this is a balanced system, terminals A, B, C, if you call this V, and then this current is I, we know that this V in here would be 120 degrees having a phase shift with this V, right? So if you just consider the V and I in the A phase, then your P, or active power, would be 3 times of V times I times the cosine of phi, where phi is the angle of voltage minus the angle of current in that phase. V is just the magnitude of V bar. But if you're having, you can express the same thing. Instead of expressing that in terms of V, you can express that in terms of V line to line. How does work? How does that work? That's because you know that V line is square root of 3 times of V, right? So therefore, if you just substitute V equal to VL over square root of 3, then that basically is found. So either this or that. But keep that in mind. When we're talking about this phi, and we're using this formulation, this phi is not the angle between VL phasor and I phasor. It's the angle between V phasor and I phasor. And same thing can go to reactive power. So for reactive power in the place of, instead of cosine, we use the sine. So P3 phase would be square root of 3 times VLLIL cosine of phi. Q3 would be square root of 3 times VLLIL sine of phi. And also keep that in mind that these definitions for the power are based on the fact that I and V are expressed in RMS form. So there is a difference between this representation and this representation. Remember, when we talked about a voltage, let's say a voltage in phase A in the time domain, that was V max some cosine of some omega t plus something, right? And when we represented this as a phasor, we said VAN. We usually made it with a capital word instead of small word, small letter, capital letter. And then we said this is VM over SQRT of 2 with the angle of whatever phi is in here, whatever theta, for example, is in here. This is VRMS, right? So this is how we usually work with RMS values rather than the maximum values in power systems. So with that, if you're saying, if you want to represent basically P 3 times VI cosine of phi, if you recall that. If you want to represent that in terms of the maximum values, then that would be 3 over 2. V max times I max times cosine of phi. So that would be the difference. And if you want to deal with the balanced power system, an easier way to deal with that is to change it into a single phase or single line equivalent. So this means that you can just consider one of the phases and then do whatever you want to analyze on that single phase system, and then extend the results to the other 2 phases, because the other 2 phases would look alike except for that phase shift for the voltages and currents, right? So this way you can deal in a much easier way with the complex diagrams for the 3-phase systems if they are represented as single phase equivalents. What you need to do, however, when you are having basically systems that have delta components, you would need to do what? Convert that delta into an equivalent Y. Because you cannot separate the 3 phases. So let's say you want to analyze this system. Okay. So the good thing about single phase is that you want to deal with one phase. But here, let's say if you want to deal only with phase A, then if this is delta connected, you have to go through at least 2 more phases, 1 more phase and then come back, right? So you have to consider both phases. So that's really ruins everything that was good about a single phase equivalent. So that's why we would need to convert this y delta into a y like this. And then this way, now it goes all the way to the neutral point and neutral point. You would need to analyze this. And these two neutral points are the same also because they have the same potential. They have the same voltage. Voltage would be 0 for the neutral points in a balanced system. So that's what you need to do.